Thanks for sticking around for the last talk of the day, as always. Thanks for the organizers for being here. This is for the invitation. This is a very interesting workshop. This is my first IPAM, and so I usually don't give talks to this sort of particular mix of scientists and mathematicians. Usually it's either like quantum information people or electronic structure people. There's usually not that much overlap. My background is electronic structure. I worked on the n-representability problem, and then in 2016 I decided I should go work on quantum computing, which was a weird move for a postdoc, but here I am. Many years later. So this talk is going to be about fault-tolerant quantum computing algorithms. It's going to be about simulation of molecular systems, but a lot of the algorithms here actually extend to other cases as well. That's really one of the things I work on at Google quite a lot, is trying to figure out precisely how we use quantum computers to get a computational advantage simulating nature. I usually like to tell people quantum computing isn't some like magic black box that spits out ground state energies. We know it's QMA complete to generically simulate ground states, and so we have to be very careful about how we construct algorithms and then import ideas from electronic structure, from other areas of physics and simulation to get efficient quantum algorithms. And so there's going to be three parts of this talk. There's going to be the first part, which is really background on quantum computing and setting up some of the infrastructure I'm going to need to explain really the main ideas. I'm going to spend the middle part talking about this notion of spectral amplification. It goes back to 2011, really, with Rolando Soma and Sergio Bourgeois. And then I'm also going to talk about its need for a sum of squares representation. And I'll talk a little bit about how we construct those and their relationship to the moment problem and representability and things like that. I care a lot about estimating how fast these algorithms are for flagship chemistry problems. And so I'll very briefly talk about circuit compilation, but I know this is not necessarily the group that cares that much about like counting the details of the gate implementations of some of these primitives. So I'll just sort of talk about this stuff very quickly, but also show some estimated runtimes at the end. Okay, so this is an interesting group that's a mix of chemists and mathematicians. I have one slide motivating chemical simulation. We know exact simulation is very expensive. Effectively, we can write down a Hamiltonian that has polynomial cost to write down. It has a polynomial amount of information, even though the Hamiltonian matrix itself, assuming a Galerkin discretization, assuming a basis, is exponentially large. And therefore, if you're interested in exact ground states or the lowest eigenstate of this particular Hamiltonian, it gets very, very expensive very, very quickly to simulate on a classical device. And there's lots of really interesting motivations for getting high accuracy simulations of nature. One that's talked a lot about is this FOMOCO example. This is the sort of business end of a little bacteria that fixes nitrogen from the air, and it does this very efficient, or it does this sort of at room temperature, and we'd like to understand that better. This would go into something like ammonia production, which we currently spend 2% of the world's energy on. There's also lots of other chemical simulations that are interesting for other reasons. Drug design, this is like a nice anti-target that shows up in a lot of drug design, that you need to make sure that your drug doesn't get removed by your body too quickly. There's already cathode material design things. And really the point of all these examples is that you can boil a lot of these down to questions about differences in ground state energies of particular Hamiltonians. So the chemistry all might be different here, but a lot of the time we boil them down to a question of what is the energy of a particular configuration of atoms, and that's sort of the setup. Okay, so I'll jump right into quantum computing and algorithms. So the idea now is I am interested in provable algorithms for ground state preparation, and the one that I'm going to focus on for this work is the phase estimation algorithm. This was introduced by Kitaev in 1995, and the setup is as follows. Let's say you're given some unitary, can be exponentially large, but just some unitary that acts on a d-dimensional Hilbert space, and it has eigenvectors that go as maybe psi with some label, and it has eigenphases. It's unitary, so it comes as these phases. And you would like to understand, or you'd like to determine what phi is. And the QPE algorithm gives you an epsilon close estimate of phi with some probability 1 minus delta for positive epsilon and delta using this many queries to controlled versions of the unitary. Okay, so what does that mean? Effectively, is that if I have some quantum system, that's this psi here, some state in the Dirac notation, and I have some other state that I initialize as zeros here, you can think of this a little bit like putting in the zero momentum mode, doing controlled operations which encode a individual bit of the phase. Now this phase is an eigenstate of my unitary into each of these qubits. And then the inverse QFT, since I was working in momentum space, just reads this out directly into something that I can measure. It's a deterministic process. So sort of in the more compact representation, I can write down my entire QP algorithm with these guarantees such that I can give a unitary, some ancilla space, and it will output some bitwise estimate of the eigenphase. Okay, so this is sort of the protocol that I'm really interested in. Notice now that the precision will actually change the number of qubits I need here. And so the cost of my phase estimation will really go as the precision epsilon that I care about. And that's a little bit different from a lot of computational setups usually on a classical computer. You really have logarithmic dependence on this 1 over epsilon, and so you don't really think about this very often. In quantum computing, almost all of the algorithms we will talk about, or you'll hear people talk about, really have some precision guarantee. And here's like the confidence interval version of that. There's a question back there.
Yeah, so if you're encoding the epsilon psi phase in like these multiple qubits, are you just doing that in like a regular floating point representation, or?
This is going to be in fixed point. It's in fixed point. Floating point doesn't have like a nice power of 2 representation, and that's really what we're doing here. We're encoding each bit. This is why the number of times I have to apply this controlled unitary is growing as a power of 2. Effectively, I'm saying for this evolution, I want to learn the to the nth bit of my phase. Yeah, that's how we do it. This is actually in this setup. This is assuming that I can actually represent my phase with m bits directly. In the case it's not, there's a slight change, but that's a small minor detail. Okay. So that's just phase estimation where I give you an eigenstate of a unitary. So that's not very interesting if I'm interested in figuring out what ground states are, because that's the whole point of this program, is for me to figure out what the ground state is. But if I have a state that's pretty close, I can take a state now that I expand in the eigenbasis of that unitary, and it's going to have some amplitude, and hopefully this is large for my ground state. Then I can apply the same thing, because it's a linear operator, to this new state and see that indeed I will get, actually I shouldn't have put this 2 here yet, because that's the output after measuring. You'll get an amplitude associated with the particular eigenvalue with a particular eigenstate. And so after measuring, you get this square. And so the probability of success will be related to the overlap of your input state to QPE. And therefore, we have to prepare an initial state with good overlap if we want to use this for ground state estimation.
I don't understand why it's a square.
This one should not be a square.
Okay, sorry.
That's what I'm saying.
Okay.
This should not be. This is a typo. This should not be modulo squared. It's squared down here. That's the probability, right? And so here we have a probability. The units are working out properly. Yeah, this is the incorrect unit. It should not be there. Yeah, so there's a bunch of questions now about whether this is applicable to interesting chemical systems. You have to know, well, generally, how many bits of precision am I going to need, right? And for us, we have nice benchmarks for this. It's sort of chemical problem dependent, how much accuracy we need. But a nice benchmark that we use is chemical accuracy, just because this is something that was decided a while ago. But this is going to depend on the chemistry that you want to study. There's also the cost of implementing controlled versions of U, right? This isn't a query model. All I've told you is that I will need this many queries to controlled unitary. I need to know if it's super expensive to implement exponential versions of this, right? And so all of that is actually something that we usually do in our group. We compile specifically the controlled unitaries and ask if we can prepare initial states with good overlap through, and we study this through numerical extrapolation. and then also just determine total runtimes. Okay, so you might ask where I get a unitary, and the constraint is that that unitary must be some function, simple function of my Hamiltonian. A natural one would be the propagator for the system, right? So e to the IH, right? That's a natural one. The eigenphases of my unitary are very simply related to the Hamiltonian. In this case, the function is identity. But I could take other simple functions that I can reverse. In fact, that's actually in the original Kitaev paper. He doesn't take the identity. He takes a different function for the discrete log problem. And so modern forms of phase estimation actually don't directly try to synthesize the propagator through some protocol. They're actually using some other infrastructure called block-encodings within the linear combination of unitary approach that builds something that's related to Chebyshev polynomials of my Hamiltonian. So sort of as a background, I'm just going to tell you some things about block encodings, and then I hope you take these theorems, just sort of put them in your pocket and keep it in mind, because I think going through all of this infrastructure is a bit much for time and this audience. But a block encoding effectively is putting some matrix that you care about in the top left corner of a unitary. Now this normalization, of course, needs to be less than 1. If it's going to go into a unitary, right, you can't just put an arbitrary Hermitian matrix there because there's a L2 norm constraint on the rows of the columns of this unitary. But you can always divide this operator A, or this matrix A, by some constant such that this whole thing will be normalized or behave as a unitary. And a block encoding is such that this is the same statement, that I'm just putting this A in the top left corner with this normalization such that that I can make a unitary actually. And what I'm going to just tell you is that there's a protocol actually for using block encodings to generate particular block encodings of Chebyshev block encodings of your underlying operator. And so let's just take the definition of a Chebyshev the Chebyshev functions of the first kind. You can make a circuit construction that effectively will block encode these functions for you given some operator. So that's all that I think we should take away from this. We have some efficient way of getting Chebyshev polynomials, which is a nice thing that we're going to have to use to, for example, do phase estimation on. We could choose a particular function, a particular Chebyshev polynomial to do phase estimation on. And that's actually the way that people generate in modern quantum algorithms the propagator, for example. They'll expand it in a Chebyshev basis and represent it that way. Yeah.
Yeah, so in your problems, do you have a canonical choice of the block encoding?
There's a lot of freedom. No, I don't. That's like this game. There's a game that we play actually importing a lot of tricks from electronic structure to make more and more efficient block encodings for a particular problem.
So I'm asking because, if A is local, a priori it's very difficult to find a local U, right?
That's right.
And so that's why I'm asking. I mean, essentially you answered the question. There have to be additional tricks.
That's right. So this block encoding is very flexible. Within this framework, what we actually require is that the Hamiltonian is represented as some linear combination of unitary form. So if you have a Hamiltonian that's represented in this way, so for example, if I take second quantized operators and I perform the Jordan-Wigner transformation on them, then I get back a bunch of Pauli operators. So this will give me some unitary representation. It doesn't have some guarantee of locality yet because I'm assuming the Jordan-Wigner representation, but this gives you a ton of freedom. You can choose really any set of unitaries here and define their weights. You can always move minus signs into the unitary. And as long as you can write down your Hamiltonian in this representation, you can build a block encoding for it. It might require some cleverness in terms of compilation and constructing the circuits that will implement that, but you can do it with enough knowledge of how to program a quantum computer effectively. There's two things that are important to understand about our phase estimation target using block encodings. Using this LCU, where you have a linear combination of unitary representation of your Hamiltonian, you can define two oracles that we call select and prepare. Now, select and prepare effectively are making sure that you can project and put your operator as the top left corner of a unitary. But there's something else that is interesting about this. When you combine this with a reflection, select and prepare are actually reflections here. And the product of two reflections now you can think of as applying something like Jordan's lemma. And Jordan's lemma lets you take the product of two reflections and then write down the expansion, the eigenbasis of your underlying operator in 2x2 and 1x1 Hilbert spaces. Okay, so that's just a linear algebra trick, but it sort of lends credence to the name of qubitization, which is sort of this overall protocol, is because we can effectively write down a new operator where within the 2x2 subspaces, we know that this unitary, this new operator, this walk operator, which is the product of a block encoding and a reflection, transforms as the arc cosine of the Hamiltonian divided by this normalization constant lambda. The normalization constant there is just for the block encoding. It's so that we can put our Hamiltonian in the top left corner of a unitary. Okay, so you'll see circuits like this, but if I do phase estimation on this guy, which is no longer just the identity function of the Hamiltonian, right? It is a nice function that is invertible. It gives me phases that I can recover, and then if I just apply the cosine function to them, which is a nice even function, so I don't care about the signs, I can get an estimate of the eigenphases associated with h over lambda. Lambda is a big positive number. It's the positive number that lets me put my Hamiltonian in the top left corner of a unitary. So since I've divided my Hamiltonian by some constant, and I want to know the eigenphases to fixed precision, that means the number of queries that I'm going to need to that fixed precision is going to go by that constant, right? So this is a very important quantity because the bigger that lambda is, the more expensive my phase estimation is going to be. I haven't talked about actually building any of these circuits for a particular representation of a chemistry Hamiltonian. All I've said is that if the larger that this norm value is, lambda, which is the sum of these weights, the more expensive your phase estimation is going to be. And so a goal is now going to be finding a LCU, a linear combination of unitary representation, that makes these W's as small as possible. And that's where a lot of the freedom comes in. And this is where we sort of import a lot of ideas from electronic structure.
Nick?
Yep.
So the L is still the bit register?
No, this is just the number of terms in your LCU. Sorry. Before, I think I called it M, and I might have changed it to. But this is just the number of terms in this expansion. So if you just take the two electron integrals, it's a 4 tensor, and you just apply Jordan-Wegener in the most naive possible way, then you're going to get n to the 4 polystrings back. And so L would be n to the 4, right? But that's a very bad LCU because that's a lot of terms in this expansion. Okay, so using this infrastructure, costs have been coming down since really since 2017. That's like when we really started, because there's been a bunch of algorithmic work on how to implement phase estimation for interesting chemical systems. They were mostly looking at asymptotic arguments. But starting in 2016 and more recently, we've gone through this program of compiling using representations like qubitization and this LCU representation that I was just talking about to give real estimates of gate costs and physical qubit costs to implement a ground state preparation protocol. And so the costs have been coming down. This is in 2019. We have a cubic scaling in basis size. There's also an epsilon there, of course. And for something like FOMOCO, that example that I discussed earlier, the basis size here, we're going to pick some set of orbitals, some local orbitals. That's going to be this n. And it's going cubically in that cost. That's pretty nice. It's close to mean field scaling in that sense, except for this epsilon. But if you compile this to gates, this would be sort of asking if you had to program your classical computer and tell it exactly how to do all of the for loops you needed to run an exact diagonalization calculation. So of course, it's like on a classical computer, there's way more work going on in the background, but your compiler takes care of that. And right now, we have to compile these algorithms by hand. Okay, so the reason I personally care about these constant factors and specifically compiling down algorithms is because the cost of implementing quantum error correction, which is going to be needed to implement 10 to the 9 gates, is very, very high. So one sort of representation of this is let's take a look at the classical NAND gate and its space-time volume. It's about a transistor nanosecond, and this is a component of the universal gate set for classical logic. If we look at the quantum version, which is a Toffoli gate, The space-time volume is very, very large. This is sort of a requirement of quantum error correction that we're trying to work to bring down. But if you just take the recent or sort of almost recent representations of the best ways to build these, this has a large space-time volume. This is actually a representation of a quantum circuit in the error correcting code. You read it from the bottom up, but effectively each of these like bars is what a qubit is doing as a function of time. So the point of this is that even if you have an algorithm that has some better asymptotic scaling in quantum versus classical, if that polynomial advantage asymptotically is not particularly high, for example, if you have a quadratic advantage, which would be like a Grover advantage, you would need to go to extremely large problem sizes to see a computational advantage, considering this massive difference in constant factors coming from implementing error correction. So we're very interested in exponential speedups, but quadratic speedups are pretty difficult to justify when you look at the actual runtimes. Okay, so like I said, a lot of these we do the busy work of compiling them down. If this is a whole separate talk, so please come talk to me if you're interested in circuit compilation. But that's really not. I don't want to talk about that now. This is just a summary for this FOMOCO problem, how we've been progressing over the years. We started in 2017 as about a century of runtime. This assumes some surface code. This is assuming a surface code with some parameters that we actually think we can make by the end of the decade. And then if you can just back out actually the runtimes based on the gate counts, and it comes out to be about a century. And over time, we've brought this down. This talk is really about these 2 points down here. And so that's a pretty big improvement, I think. Again, we'll see how it all pans out when we actually have the devices to run them on. OK, so I'm going to switch over now to spectrum amplification, which is really the core idea here. Spectrum amplification is a pretty simple idea, actually. Let's say that you have a dependent variable y and an independent variable x. Right? And you're interested in estimating what x is, but you only have access to samples of y. Okay? So the way I've set this up, you might suspect that I'm going to go to something like error propagation, and indeed you're correct. For this particular setup, if you want to recover x from estimates of y, your uncertainty on x actually improves as your value of x gets closer to 0. So how do you see that? Like, well, if I estimate y, I need to square that thing. And so I'm squaring y plus or minus the standard deviation of my estimate. And so to first order, that thing is getting very small if x is very small. It's just expanding out that quadratic. So what this tells you is that if you pick your function correctly, you can actually use error propagation to really benefit in terms of error propagation. And like I showed on the first slide, we care a lot about in-phase estimation, about setting our epsilon. And so that dictates the cost. And so if I can pick a function for phase estimation that has an efficient representation of the block encoding, and I can exploit this property where error propagation helps me, I can potentially have a very large algorithmic win. And this is actually an idea that you can apply in all sorts of places. And this is introduced in 2011, but it probably came up in many other areas. Another way to look at this is that if you're interested in estimating quantities that are close to 0, then you can get a quadratic advantage effectively by this same argument. Okay. The way this would work for a quantum setup is a little bit different. It's not just the square root. We need something that is the square, right? And so what our input is going to be is some Hamiltonian that has this particular sum of squares formed. Okay. What I can do is actually make a Hermitian dilation of this Hamiltonian such that I have a square, under the square operation of this HSGA, which is called a spectral gap amplifiable form, I can recover a block encoding like thing which represents my Hamiltonian. So all I'm doing is defining some Hermitian dilation that I can square and recover my Hamiltonian, at least in this subblock. You can show, just like in the block encoding setup, that this is invariant in a particular 2x2 space. You can diagonalize that and show that indeed for the Hermitian dilated Hamiltonian, the eigenvalues of that are the square roots of my underlying Hamiltonian. So you can ask if I just did a singular value decomposition in a really complicated way, and indeed asymptotically these are sort of equivalent. This is just the Hermitian dilated form. Okay, so if I give you block encodings to each of these B's of the sum of squares operators, then you can go through the same LCU protocols before and the same phase estimation protocols before, and you get out a new effective lambda. That new effective lambda, just like in our little square root of x estimation function, is going to depend at first order on the block encoding lambda as before to make it a block encoding, but now also the eigenvalue itself. This is just from squaring y plus or minus sigma y, right? The y shows up at first order in that square, right? And so now I have some error formula that depends on my eigenvalue that I'm estimating. So that doesn't seem very good. But this is a positive function, and if I have an upper bound to this, then that tells me an upper bound to the queries, and that's still a valid cost model. Okay, so that's precisely what spectrum amplification is doing. If I can prepare a Hamiltonian that is related to my desired Hamiltonian as a sum of squares, which if people were around for Eugene's talk, we will know that we can do, I can get a quadratic advantage, or close to that, because now this HSGA has a square root in front of it. If this E alpha that I can bound is close to 0, which is going to be the E alpha of this new sum of squares Hamiltonian. Okay, so can we do that in chemistry? Yes, we can. That was the topic of Eugene's talk. But if you're more familiar with moment methods or outer approximations or trying to think of other names that go under non-commutative polynomial optimization, writing down a sum of squares Hamiltonian that is a witness to the lower bound of the eigenvalue of a particular Hamiltonian is indeed the dual problem of the moment problem. And so this goes by different names in different communities. Chemists like to call this n-representability. Quantum information people call this the NPA hierarchy. They also call it the quantum marginal problem. But they all generally have this very nice hierarchical form where if you have an algebra that is, if you have an algebraic ansatz representing each of these O alphas, and you expand that in some order, so like the many-body order of each of these O alphas, then there will always be this hierarchy that's satisfied. The version of this before from Eugene's talk was making the sum of squares ansatz in the fermionic ladder operators larger and larger many-body order, so involving like one-body operators, two-body operators, three-body operators, and so on. You can include this with, or you can show this in the set inclusion form, which is normally how it's done in the sort of non-commutative polynomial optimization, but it all sort of carries over the same. Okay, so you can ask about the eigenvalues of this sum of squares. And if I have a lower bound, or if I compute this sum of squares and this lower bound, then this E gap is precisely the ground state of the sum of squares representation. So this E gap, this ESOS, is precisely the E that was appearing right here. And so our goal is to make a sum of squares representation with as tight a lower bound as possible so that we can benefit from the fact that this appears in our error propagation formula. So it's sort of like a simple trick, right? But it requires like all of this extra infrastructure, which is sort of funny. There's a notion of frustration freeness here, the CS version of frustration freeness, that if we have a perfect sum of squares, let's say I figure out exactly how to write down a sum of squares, then for the ground state of the Hamiltonian, of this Hamiltonian, this term will be identically 0 if I evaluate that expectation value, and it will be term-wise 0. And so that all that would tell us is that indeed the lower bound that we estimated as a pre-processing for this, the sum of squares lower bound, is the eigenstate. So we want to make our Hamiltonian a sum of squares representation that is as close to frustration-free as possible. And that's sort of this connection between the sum of squares hierarchy and spectrum amplification. We're using both of those ideas to potentially get a computational speedup if we can write our chemistry Hamiltonian in this form, and indeed we can find a small gap. So there's a lot of caveats there. It's not clear that this is possible at all. Okay, so The computer science community would like to know if this pre-processing is exponential or polynomial cost. Indeed, it is polynomial at fixed k. I can cast this entire sum of squares optimization as some semi-definite program. Here I've written it in a quadratic representation where here's some Gram matrix. O are some vector of the basis for my algebra that I'm going to expand this sum of squares in. Here's like an ansatz for what the O alphas are of my sum of squares. And then I just solve the semi-definite program where I maximize the lower bound. And so that's sort of the entire discussion that Eugene had yesterday. Okay, so it is indeed for a constant k, a constant size sum of squares, polynomial preprocessing. Okay, so how does this do for chemical systems that we care about? Remember, we have to show that this has a low enough, a gap in the SOS spectrum that has a low enough values that we can actually computationally win. And so let's say we are constructing an SOS of this particular form. We have some linear mode operators, and then we have this guy here. This is a one-body operator, and this identity here is actually included in this algebra for a particular reason. You might think, well, this identity, to include this, I'd have to lift a particular Lie algebra to an enveloping algebra, but that's actually OK here. I can map this identity back to the whole form of this guy. It's all OK to work just in the ladder operator formalism. The point of these numerics here is that we implemented that some semi-definite program on the previous slide, and we looked at the lower bound value. And these are in Hartrees. And so if you're a chemist, you might look at this and say, well, I care about chemical accuracy, which is, in this unit, 1 times 10 to the minus 3, approximately. And this is 4, ish, 2. That's really bad. But remember, we don't care about the lower bound accuracy in a chemical sense. All we care about is its relationship to the query complexity for phase estimation. The equality here is always satisfied. So I have a sum of squares that represents my Hamiltonian with some shift E lower bound, right? Again, that's just a certificate on the lowest eigenvalue of this particular Hermitian operator, okay? It's just asking whether this inequality is true in some sense. Okay, so these are terrible energies for chemistry. What I care about actually is ESOS, and whether this actually also relates to a small lambda in the sense that I can block encode this thing efficiently. Okay, and that's sort of the rest of all of the detailed work of this talk, of this work, is that you sort of go figure out a particular representation for this related to this particular SOS, and then figure out if you can block encode that efficiently. And of course, I wouldn't be here probably telling you about this if we couldn't do this. We can do that efficiently, and we do get a very large computational speed up because of it. Okay, so this is sort of an aside. The Hermitian dilation that I was showing you before, the spectral gap amplifiable form, and I made this sort of side comment that this might just be related to singular value representation. Indeed, you can show that you don't need to do that Hermitian dilation if you just have rectangular block encodings. So in the block encoding, I was putting an operator up in the top left corner, but there was no need for it to be square. You can show that you can do a rectangular block encoding, and effectively building a walk operator requires 2 calls to this block encoding. The way to understand that is if you write down a matrix and you decompose it to its left and right singular values, if you just apply the Hamiltonian in that form, the right singular values get mapped to the left singular values, right? That's just the Bra and Ket representation of right and left singular values. So you have to apply this twice if you want to stay with the right singular values of your system, and so that's sort of what we have to do here to make everything work out. If you're a quantum algorithms person, you can actually recover all of this from QSVT, quantum singular value transform, but it ends up being a little bit more expensive or complicated. So this double application of this rectangular block encoding, turns out, is actually just a block encoding of the second Chebyshev polynomial. It ends up being this guy of my sum of squares Hamiltonian. So that's why I brought up Chebyshev polynomials earlier. And if you go through the error propagation formula, namely, I differentiate to first order, I differentiate this guy, and I look at what the inverse of that derivative is, it looks exactly like the sum of spectral gap amplified error, except it has a factor of 2 missing. You can show that this type of block encoding, namely the second Chebyshev polynomial form, is optimal for sum of squares operators. It's like a couple of lines showing that out of all of the Chebyshev polynomials that I could build with a particular block encoding, this one will give me the minimum cost. Okay, so you can do this. You can sort of set up this infrastructure with these rectangular block encodings. You don't have to do a permission dilation. You do get some savings there. The circuit diagram representation, the toy circuit diagram representation, effectively has this very, very simple structure. It's known by a lot of different names, this circuit structure. It is one iteration of oblivious amplitude amplification. It is one step of qubitization. It is also known as a block encoding of the Chebyshev polynomial. All of those are exactly identical names for this particular protocol circuit-wise. But I just want to emphasize again that if you go through the error propagation formula, you just define a new number of queries to your walk operator, which is going as the square root of your lower bound energy on the sum of squares Hamiltonian and your new lambda for this setup. Okay. I don't want you to really try to understand this slide. It's just to show off that we actually compile these things. This is a very tedious component of this, and we are working hard to automate this. But we do count all of the operations needed to implement the block encodings for these things. Okay. I sort of lied to you a little bit. We don't precisely implement the sum of squares we get out of the semi-definite program. We do a bunch of other things to try to minimize the lambda associated with the block encodings for each of these. These are our sort of chemistry tricks. It turns out you can combine double factorization and tensor hypercontraction for the chemists in the room and make a sum of squares Hamiltonian with it. And then we numerically optimize to try to find a sort of a ghetto version of the semi-definite program. Since I personally think solving semi-definite programs is a bit of a boondoggle. They're very slow mathematical programs. Okay, so now the performance. How does it actually work out? Remember, I've combined this idea of spectral amplification, which requires a sum of squares representation. I've constructed a sum of squares representation in a very, very simple algebra, which has sort of a bad lower bound. But it does mean that I can get a good lambda for these systems. And the things that I want to point out here are actually on the bottom. These are the improvement factors in the total costs of running phase estimation for these molecules with respect to the best literature values I could find. And so in some cases, we're about 2 orders of magnitude better. In other cases where people have tried harder to optimize the algorithms, we're 4 or 5 times better. And we didn't really try to optimize all of the cost here. Like I said, we picked the sort of a very simple sum of squares representation. There's lots of games that we can play about defining what the correct point in the SOS hierarchy is to use as a representation of my Hamiltonian. I could use also multiple, I could use pieces of level 2 and I could use pieces of level 5 if I wanted to. But this gets into a game of trying to construct a mathematical program that optimizes over all those things to find a good lower bound. And that's also a challenging thing you need to optimize for. But with this first pass, we got pretty good improvement. I will say also there's a way to bound how far our effective lambda is from optimal. The lambda is effectively, like I said in the block encoding, telling you how you can take a operator and put it in the left corner of a unitary. The optimal way to do that would just be look at the spectral norm of that operator, figure out what that is, and divide by that number, right? Because that's exactly telling you the minimum number I need to put this in this top left corner. And we can get a lower bound on that number, which will tell us a lower bound of lambda effective pretty easily from electronic structure calculations. This is just actually a Hartree-Fock calculation on the Hamiltonian and then Hartree-Fock on the negative of the integrals. It's a pretty neat trick. And we're within a factor of 2 of the optimal lower bound, or the optimal lambda for this particular SOS representation. The very interesting thing about this is that we get an asymptotic improvement from cubic to quadratic, which is pretty nice. This is empirical. We didn't prove this. We will have a paper forthcoming that does prove this for a particular condensed matter system. I think it's probably not likely we can prove this for a general electronic structure system. we get a very large speedup using this combination of tricks, the sum of squares representation and this notion of spectral amplification. And then if you compile this to the surface code for one of these, if we compile to the surface code and we look at FOMOCO again, which was that thing I was showing you on the original slide where the cost of coming down from a century to about 8 hours, there's some details about implementing those Toffoli factories I was talking about, but this will run at about 8 hours and 4 million physical qubits. And
can you specify exactly what n is?
N here? N is the size of the basis that I'm using to represent the Hamiltonian.
So not the number of qubits?
It's not the number of qubits. The number of qubits I need to represent the system would be 2 times n. But in all of these LCU algorithms, the number of qubits, logical qubits I need to represent the block encoding is much, much larger than that, generally. Remember, the unitaries are a dilation of the space themselves. And so,
much more than, is it much more than a couple times n? Or
so these numbers up here.
Oh, because of the L, right? I mean,
it's because of the L, right?
N.
The additional, there's a couple of ways that ancilla qubits are needed here. There's the L for the block encoding, right? But we also use these tricks where we can trade space for time in a lot of the algorithms. And so we will blow up our space a little bit to save Toffoli complexity. Yeah, so it's a little bit of, it's hard to directly map. So these are the number of orbitals in each of these systems. And to represent the quantum systems for each of these is just twice this in terms of the spin orbitals. But the way that we implement our block encodings requires a logical qubit overhead, which can be considerable. And so let's just look at the FOMOCO example that I was showing. This is a 76 orbital example. I need about 1,500 logical qubits to do this. So that's about an order of magnitude more than representing the system. The dominant cost here is actually qubits that store outputting the representation of this Hamiltonian. So each of the Hamiltonians, there's a bunch of coefficients associated with them. And the way that we implement those in the circuit is we have to output all of those coefficients. This saves in the number of rotations that I need to do. But that storage of all of those coefficients costs quite a lot. And so there's a bit of overhead for that.
Sorry, and how do you find lambda?
The lambda is the summation of the absolute values of the weights of the LCU. So it's probably hard to see in this representation. Well, here, these E's are our E's. These are the unitary group generators, EIJs. The weights now would be the absolute value of all of these guys summed up. Each of these EIJs I can implement as Majoranas, which are unitaries. And so I transform each of these ladder operator representations to Majoranas, and then I implement each of those Majoranas, and then that's my LCU.
But the lambda is from, classically would come from maximization of the Hamiltonian.
Lambda. So one thing, like for example, I could create a LCU representation just on density fitting, right? So let's just take my 2 electron integrals and I decompose it, I do a Schmidt decomposition, or I eigenvalue decompose it, right? This is some positive spectrum. All of those I can implement each of those terms in the representation of the 2 electron integrals with a weight according to the Schmidt weight, the Schmidt rank there. And so that's one way to do it. But there's lots of other ways. I could do a tensor hypercontraction version of this too. In fact, THC is a very nice compression. It's just hard to find a THC since that's a CP decomposition, right? But with that representation, I can really compress what the lambda is from that. But asymptotically, I don't think lambda is ever going to be better than, in this representation, it's never going to be asymptotically different than a quadratic function of the number of electrons, because it's the Coulomb operator, so it's got to count up all pairs. So it's a little bit detailed. Like the details of the block encodings for a particular representation of the Hamiltonian sort of are separate from the sum of squares part and the spectral gap amplifiable. If I just present to you, if there's like a single takeaway, is that if you have a sum of squares form, you can apply this spectral gap trick. And it works if your lower bound is really tight and you have an efficient block encoding. But the details of how you do the block encoding, that's all very, very detailed compilation work on the quantum information side. The algorithmic side is just these two simple ideas. Okay, yeah, so I'll probably just end there. I think there's a lot of places that this can work. We know that this also gives you optimal time evolution if you are restricted to a low energy subspace. So you can show in a similar fashion, there's a much longer paper from a year ago with Rolando, where you can build the propagator if you're very, very efficiently with a quadratic improvement if you are restricted to a low energy subspace. Again, this idea that if you're close to the ground state, you can exploit that fact. We can also show that you'll improve measurement costs if you use this trick in that context for eigenvalue or expectation value estimation. Okay, I'm happy to take questions.